The response variable is the one that is being affected or responding to the other variable. So in this situation, we're trying to see if fertilizer can affect the crop yield. So the response, what's being affected or responding, is the yield of the crop, and how we can predict what that yield is the amount of fertilizer that we use. Let's look at another one here, this one with a negative relationship. As one variable goes up, the other one goes down. That's what we mean by negative relationship. So what is responding here, what is being affected, is the amount of candy that is received. And what can help us predict the amount of candy received is the age of a child. So as they get older, the amount of candy they receive goes down when they go trick-or-treating. And even if the relationship is not linear, our predictor and response variables are still going to be set up the same way. The thing that's being affected or responding in this case is total profit. And what is predicting the total profit and kind of driving the relationship in this case would be price. So that would make it our predictor variable. A linear model is going to be appropriate as long as the points generally follow a straight line pattern. Like in this case, they're slowly going up from left to right, like the line is, so a linear model is appropriate. We want to make sure there's not some other pattern or distinct shape that they're following. This would be appropriate for linear. This one's not, because they seem to go up at the beginning, but then they stop following that straight line pattern and take on a new shape. So this would not be good for a linear model. For a question like this, if we're actually trying to find the equation here of the line that's drawn, we need to fill in two numbers here in the equation. It's actually the two numbers we're going to find up here as well, the slope and the y-intercept. The equation is in the form y equals mx plus b, slope-intercept form. They actually have it listed here with the b, the y-intercept first, and then plus the slope multiplied by x. So once we find these two values, we can just plug it in here and we have the equation. Now what you want to do is look at the line and try to find 2 points that are on the line that you can easily figure out what the coordinates are for those points. Now one is the y-intercept. It crosses really nicely here. It looks like at 21,000. So the y-axis starts at 19,000, 20, 21,000. So 1 point on the line is 0, 21,000. And then another point on the line that you can easily identify what the y and the x coordinate is this is probably the best choice here. X is 9 and y is 24,000. Anytime you have 2 points on a line, you can find the slope of the line by subtracting the y's on top. So 24,000 minus 21,000, and then subtract the x's on bottom. 9 minus 0 gives you 9. And then I'm going to convert that to a decimal, reduce that slope, 3,000 over 9. If you actually do 3,000 divided by 9, you get it as a decimal, 333.33. So that is the slope. If you think back to writing that equation, the slope is multiplied by x. Our intercept is then the number by itself. And that's how you get the equation of the regression line. And this one would be very similar. I do want to point out something I mentioned in the last video. We're looking for points on the line. You actually don't need it to be a point on the line. You just need to see where the line crosses really nice coordinates. So for example, like I could use this point right here where x is, are we counting up by 5s here? 5, 10, 15. X is 15. The line crosses at 15 and y is 23. So for this example, delete that word. One of my points could be 15, 23. So we're just looking for 2 points on this line. They don't actually need to be data points, actual blue circles from our data. We're just looking at the line. And to find the slope of the line, we just need 2 coordinates of points on that line. So I could also use the y-intercept here of 0, 23. So did I do that wrong there? Let's go look at 15 again. 0, 23. was 15, 5, 10, 15 is at 22, 21, 22. 15, 22, and 0, 23 are 2 points I can use. So yeah, don't get caught up trying to find a blue point, an actual data point that's on the line. Just like with any graphed line you ever see, you just need to find 2 coordinates that it passes through to find the slope, and then look where it crosses the y-axis to find the intercept. So to complete this one, if I do 23 minus 22, that gives me 1 on top, and then 0 minus 15. As you're subtracting the coordinates, make sure you always start with the same one. So since I did 23 minus 22, I need to do 0 minus 15 to get a negative 15. And my slope here is negative. You can tell by the line is going downhill, so I better get a negative result. As a decimal, it's 1 divided by negative 15. So negative 0.67, if we're rounding here, that would be our slope. Negative 0.067. Our intercept was 23. So that would be your answers, and then copy those numbers up to where they go here. For the interpretations, first you need to understand what the data is showing. So let's read this here. The scatter plot shows the relationship between the number of years a person has worked. So if they're a 5-year, 10-year, 15 employee, how long have they been with the company? That's what X is showing us. And the annual, it's kind of cut off there, salary of that employee. All right, so just looking at the trend, it looks like the longer they've been with the company, their annual salary is going up. So what's the interpretation of the slope? Slope always shows us how much does the y value change when x increases by 1. That's what the number of the slope is telling us. In this case, the slope, the number multiplied by x, is 333.33. So we expect the y value to change by that amount when x increases by 1. In context, we expect a person's salary to increase by that much when they work 1 additional year. They've been with the company for 1 additional year. So a change in salary for 1 additional year work. In this case, it's $333. That employee could expect their pay to rise by about that much for every year worked. Now for the y-intercept, you always need to see if it has a practical interpretation or if it doesn't really make sense in context. The y-intercept is always when x is 0. And we want to see what that y value would be when x is 0. In this case, x, the years worked, is 0. So you haven't worked any years with the company. In context, that would mean you're a brand new hire. You just got started there. You have put no years in yet. And so the y, then your salary, that would be your starting salary. If you've put no years in yet, the y-intercept would be what you expect a starting salary to be for an employee. Let's look at one more of these. A scatter plot showing the relationship between the time spent to complete the first project. So here's how many minutes you work on the first project. So 25, 50, 75. And then the number of projects attempted in the week. So it kind of makes sense that this is negative here. If you spend a lot of time on that first project, you don't have as much time to try to attempt and finish new projects. So the number of projects you get to tends to be going down if you're working on that first one for a long time. So slope, always showing how much do we expect y to change when x changes by 1. In this case, x changing by 1 would mean you spent 1 additional minute on that first project, and how many fewer projects do we expect you to attempt then? And it's 0.067 fewer projects for every additional minute you spend working on that first project. So the expected change in the number of projects attempted for each 1 minute increase in the time spent on the first one. Interpretation of the intercept, does it make sense in context? So can the number of minutes spent on a project be 0? Would that make sense? No, you can't complete a project with no time at all. So there's no practical interpretation in this context. So let's look at this one here. A medical researcher wants to determine how a new medication affects blood pressure. That's our context here. Really what we're trying to figure out is just what is the equation here. We have a line. We did a problem similar to this earlier. The y-intercept, the number by itself here when x is 0, the number by itself in the equation is 140. And so that is 1 point on our line is 0, 140. And then let's see what another point on the line is. And it doesn't have to be an actual data value. We just need to see where does this line cross some nice coordinates, x 150 and y 130. And then so doing subtraction, 130 minus 140 gives me negative 10. And on bottom, 150 minus 0 gives me 150. I should get negative since the line's going down. And if I do negative 10 divided by 150, I get negative 0.067. And so that's the number that's multiplied by x. And that's the equation. For this next one, our situation is we're looking at the amount of time spent on financial education. And then this is the amount of debt on the y-axis. It makes sense it'd be negative. The more time you spend learning in hours about finances, the less debt you might have. So it's going down here. Here is what we see in the data. We have the equation given to us for this line. And here we have some information. A financial education time of 21 hours is found to result in an amount of debt of $39,500. So I'm not sure if this is actually a point on there, 21. It doesn't look like this is an actual point on the data we have here, and that's fine. This is a new piece of data that we've gathered. It's not shown in the scatter plot. But this is asking us what is the predicted amount of debt. So what it's saying is we have 21, let me write this over here. We have a point from our actual data of 21 hours, and then the y value, the amount of debt, is 39,500. That's a point we found in the data. It's asking what would the prediction be based off of this equation. If we're using the equation to make predictions, what do we think y would be if x is 21? So what you need to do is put the 21 into our equation and see what the calculation comes out for the prediction for y. So 50,000, I don't know if I said 5,000 earlier, but that's it is a 50,000 minus 500 times x. So minus 500 times 21. This would be our prediction for what y would be if someone has done 21 hours of training. And look, it's exactly what the actual data point was. And so what we have here, the predicted amount is the same. That's what we calculated by plugging 21 in. And where does that fall in terms of the line? Where does the observed value fall in terms of the line? The observed value was 39,500. The predictions are always exactly on the line. We're using the line to make predictions. So the observed value here is on the line, since the observed value is the same exact result as the observed value, same exact result as the predicted value when we plug 21 in. Let's do one more of these. 34 hours has 36,627. All right, so let's put that point up here. 34, 36, 627. So just for reference, that's an observed value. We ask somebody what their debt is, how much time they spent, and that's our observation, our data. What do we get when we plug a 34 into this equation? So 50,000 minus 500 times 34. Oops, I put an equal sign in. So we get 33,000. So this is our prediction, and that's what we need to type in. What is the predicted amount of debt for someone with 34 hours? And where does the observation fall in relation to the regression line? So remember, the predictions are on the line. We're using the line to make predictions. That's what the regression line is for. So this observed value, that's more than that. That is above, higher up above the line our observed value is compared to the predicted value that is exactly on the line. And do something similar here for this next one. Plug it in and calculate when x is 39. In this next problem, we have an observed data value here. So an actual data point, x is 31, y is given here as this value. Now it says that value is actually on the regression line. When you're on the regression line, you have a residual of 0. The residual is how far away you are from the regression line. So points above the regression line have a positive residual. You take that y value and subtract what the predicted value of the line is, you would get a positive result. And you can measure how far away the point is from the line by calculating the residual. Points below have a negative residual. If you measure how far away they are from the line by taking their observed value and subtract the prediction on the line, you get a negative result. And so points below the line have a negative residual. And then in this last one, we have our data here, the regression line. You should only use regression equations within the context of the data, because they are built, the line, the equation is built off of the observed data values. So in this case, we can use this equation to make predictions as long as our x value is within this range. So for an x value, amount of medication of 350, our x is the amount of medication. 350 is pretty far outside the scope of the data. So you should not use this equation, this line, to make predictions about blood pressure for an x value that is outside the scope of the data. So anything above 300, we would say no. Anything really low, close to 0, again, no, you should not use this equation.